This is your presenter Asloob Mudassar, and I am presenting slide number 68 of the course on laser physics. Question is, discuss level occupation at thermal equilibrium in a bulk semiconductor material. The answer is, assuming a semiconductor material is in thermal equilibrium, the electrons in the semiconductor will obey the Fermi-Dirac statistics. The probability for a valence electron or a conduction electron to occupy a level of energy E prime is given by F of E prime is equal to 1 over 1 plus e to the power E prime minus E F prime divided by kT. So this is the Fermi-Dirac statistics, and it gives you the probability for a valence electron or for a conduction electron to occupy a level of energy E prime. So if E prime belongs to the conduction band, then this will give you the probability of the electron to be in the for the electron in the conduction band to occupy an energy state E prime. And if E prime belongs to a level in the valence band, then this will give you the probability that a valence electron could occupy an energy state E prime. So in both these cases, F of E prime will give you the probability of occupancy of energy level E prime by the electron, where E F prime is the energy of the Fermi level. We get F of E prime is equal to half when E prime is equal to E F prime. That is, when the energy of the electron is equal to the Fermi energy, the probability is half. That is, it is a 50% chance that the electron with the energy E prime is occupied. That is, the probability of an electron to have an energy exactly equal to the Fermi energy is half. That is, 50% chances are there that the level E prime will be occupied when it is equal to the Fermi energy. Now letting T goes to 0 gives F of E prime is equal to 1 when E prime is less than E F prime. That is, when the energy of the electron is less than the Fermi energy, then it is 100% chance that the energy level E prime is occupied, because F of E prime is equal to 1. And when F of E prime is equal to 0, this is 0 when E prime is greater than E F. That is, the Fermi level separates the filled region from the empty region. So you see that we have two values of the probability. One, when the energy of the electron is less than the Fermi level at T is equal to 0, then the probability is that the Fermi level is 100% occupied. That the Fermi level that the level E prime. So when an electron has an energy E prime less than the Fermi energy, then at temperature T goes to 0, the probability that the electron will occupy that state is 100%. And when E prime is greater than the E F prime, that is, the energy of the electron is greater than the Fermi energy, then close to absolute 0, the probability that the electron will occupying that state is 0. That is, so you see that there are two distinct boundaries. That is, the Fermi level separates the field energy. So this is the field energy region in which E prime is less than E F prime, from the empty region in which E prime is greater than E F prime in a semiconductor. And you see that this analysis is only valid for T goes to 0. So let me explain this over here. So you see that if E prime is less than E F prime, then you see that the numerator E F minus E F prime is negative, and we have T over here which is at 0. Then you see that this negative sign divided by 0 will give you negative infinity. So E will be raised to minus infinity, and E raised to power minus infinity means that 1 plus 1 over infinity, and 1 over infinity is equal to 0. So 1 plus 0 is equal to 1 in the denominator. and 1 over 1, that is 1 in the numerator and 1 in the denominator, will give you 1. So f of E prime is equal to 1. This is the case when the energy E prime is less than EF prime. In that case, the exponent raised to the power minus infinity, because t is 0. So 1 over 0 is infinity. Now the second case is that E prime is greater than EF prime. So the numerator of the exponent is positive. So when you divide it with 0, because t goes to 0, then you have a plus infinity. And e to the power plus infinity means infinity. So 1 plus infinity is equal to infinity, and 1 in the numerator divided by infinity will give you 0. So in that case, the probability, that is f of E prime, will be equal to 0. So remember that this analysis is only valid when t goes to 0. So close to absolute 0, we have two distinct boundaries. Either we have the filled region or we have the completely empty region. The filled region is the region where the energy of the electron is less than the Fermi energy, and the empty region is the region where the energy of the electron is greater than the Fermi energy. So this analysis is also applicable for an undoped semiconductor. For an undoped semiconductor, EF prime is situated in the middle of the energy gap. Plots of E prime versus K and versus E prime versus f of E prime is shown in figure number 68.1. That is in this figure. So you see that, let me read the caption: plot of E prime versus K on the left side, and the plot of E prime versus f of E prime on the right side. So you see that I have shown two bands. One is the valence band at the bottom of the left hand side, and the other is the conduction band facing upward. That is the parabola facing upward along the energy axis is the conduction band, and the parabola facing downward is the valence band. So you see that filled circles, and the filled circles in the valence band, and the hole and the open circles in the conduction band. These two bands, these two holes, indicate the possible states available in the valence band and the conduction band. The filled holes in the valence band can be stated as these are the occupied states in the valence band, and the open circles indicate that these are the open states, that no electrons exist in the conduction band, because none of them is a solid circle. And this analysis holds at absolute 0. So you see that there is also an energy gap between the two. Eg, capital E with a small subscript g, is actually the energy gap between the two levels, between the two bands, that is the conduction band and the valence band. And you see that we are plotting the energy E prime versus K. The K is in the horizontal axis, and this horizontal axis is at the top of the valence band. Because in the previous slide, that is in the slide number 67, we have set up this level. So according to this level, the energy of the valence band will be negative, and the energy of the conduction band will be taken as positive. We have also shown the situation in which an electron in the state E1 prime in the valence band is pumped with the energy h nu to a level E2 prime of the conduction band. So you see that h nu is actually the pump energy. That is, you supply this energy to the semiconductor material, and an electron with energy E1 prime in the valence band is raised to the conduction band with the states E2 prime. So this is the description that we have given for the plot of E prime versus K. Now on the right hand side, we have the plot of E prime versus f of E prime. You know that f of E prime gives you the probability that the state E prime will be occupied by an electron. And you see that we have also said one thing over here, that f of E prime is equal to half. When it will be half? It will be half when the energy of the electron is equal to Fermi energy. So you see that in this case, you can see that when the dotted line indicates the Fermi level. So when E prime is equal to the Fermi level at this, that is in the center of this curve, what will happen? It means that the probability is half over there, because the value of f of E prime is half, which means that when E prime is equal to the Fermi energy, then there is a probability, 50% probability, that the state E1, that the state represented by E prime, will be occupied by the electron. So when the energy E prime is greater than the Fermi energy, and you see that the E prime becomes greater when you move towards the left side from the central region. So from the central region where the value of f of E prime is half, if you move from center towards the left, you will see that the energy will increase along the energy axis, that is E prime will increase. But you know that at the same time you will notice that if energy increases, then you see that f of E prime decreases, because f of E prime will move towards 0. And when the energy E prime is much greater than, that is we are along the energy axis E prime, then you see that f of E prime will be 0. So when the energy of the electron, when the state with energy E prime, when the state with energy E prime has an energy much greater than the Fermi energy, then you see that the probability that the electron will exist in that state will be 0. Now from the center of this curve, if you move towards the right, then you see that the energy E prime decreases below the value of the Fermi energy. So E prime smaller than the value of this dotted line, which is the Fermi energy level. So when E prime is smaller than that one, you will see that f of E prime increases towards the right, and ultimately it becomes equal to 1 when the energy E prime is nearly 0. So when E prime is nearly 0, then the probability that the electron will occupy that state of energy will be equal to 1. So you see that this will give you the probability. The overall, we can say that the overall result is that when a state with the energy E prime has an energy greater than the Fermi energy, then the probability that that state will be occupied becomes smaller and smaller with increase in energy, and ultimately it becomes 0. That is the Fermi, that f of E prime becomes 0 at a large value of energy. But when the energy is smaller than the Fermi energy, that is we are moving towards the right, then f of E prime becomes greater and greater, and ultimately it reaches its maximum value, which is equal to 1, and this maximum value will only be possible when E prime is much less than the Fermi energy, that is when E prime is close to 0. So under that condition the probability is 1. So E prime represents a state of the electron, a state in which we are talking about the electron could exist or not. So that state or that energy, so E prime is the energy of a level, and f of E prime will give you the probability that such a level will be occupied by an electron or not, depending upon the value of f of E prime. When f of E prime is equal to 1, then it means that it is 100% chance that such a level of energy will be occupied by an electron, and when f of E prime is equal to 0, it means that there is a 0 chance that such a state will be occupied an electron. So you see that we have mentioned over Eg. Eg is actually the gap between the two levels, that is between the valence band and within the conduction band. So you see that we have shown the valence band with filled circles. It means that all the states are occupied, because these states are well below the energy Fermi energy. So since these are well below the Fermi energy, so there is a significant probability that these states will be occupied, because the probability is always greater than half in such case. But if the energy, for the states in the conduction band where the energy E prime is greater than the Fermi energy, then you see that the probability that such a state will be occupied by an electron, all these states are empty. So the conduction band, all the states within the conduction band are empty, because the probability becomes less than half. It means that less than half are the probabilities that such states will be occupied. So So now let's talk about this Eg, which is the band gap energy between the two levels, between the conduction band and between the valence band. So you need to actually provide, if you want to move an electron from the valence band to the conduction band, you need to supply at least this much energy. That is the energy at least greater than or equal to Eg value will be supplied to an electron at the top of the valence band to move to the conduction band. But if the electrons are existing on either side of the parabola, then the amount of energy h nu will be much greater than Eg value, because this it depends upon which electrons do you want to move to the conduction band. So the difference of that one will that energy has to be supplied. For example, here we have supplied the energy h nu to move an electron from the valence band with the state E1 prime to the conduction band with the state E2 prime, and you know that here h nu is greater than Eg. Okay, so as Eg is much greater than kT, you see that kT is the thermal energy available in the environment. So when the band gap energy is much greater than, as band gap energy is much greater than kT, only a few electrons are thermally activated to the conduction band, because kT is actually thermal energy available to the electrons in the valence band. The electrons in the valence band then do not have much energy to surmount the energy gap, because kT is much less than Eg. So such electrons cannot move to the conduction band. And in terms of the probability, we can say that a few electrons are thermally activated to the conduction band. Out of many electrons, only a few electrons will move towards the conduction band on the basis of the thermal energy they obtain. Now filled circles in the valence band indicate the presence of electrons, and open circles in the conduction band indicate the absence of electrons or presence of holes. Circles also indicate the available states in both bands. You know that in the semiconductor, we say that when an electron is not present, then you see that vacancy is also referred to as a hole, because a hole is created. So either we say that in the conduction band these circles, these hollow circles may be treated as absence of electrons or the presence of holes in the conduction band. So these two words, these two terminologies are equivalently used in the field of semiconductor theory. So you see that up till now we have described when the semiconductor was not doped, no doping was present. The Fermi level was lying in the middle of the valence band and the conduction band. And the analysis so far we have given up to the occupancy of the states and the calculation of the probabilities was on the basis that time that the temperature goes to zero or close to zero. And we have discussed the two cases, that the energy, that a state with the energy less than EF prime and a state E prime with the energy greater than EF prime, and with the respective probabilities equal to 1 and equal to 0. Now we are talking about the doping of these semiconductor materials. With N-type doping, EF prime is displaced towards the conduction band. That is, if you have an N-type material, that is, you have doped the semiconductor with N-type material, then what will happen? This Fermi level EF prime shown in the dotted line will move towards the conduction band. And if the doping is very high, then even this EF level can also lie in the conduction band. And if you are doping it with the p-type material, then you see that this Fermi level will move downward. And if the doping is very high, p-type doping is very high, then you see that this Fermi level can even penetrate within the valence band. With N-type doping, EF prime is displaced towards the conduction band, because then we have an excess of electrons available in the valence band. That's why the EF energy level will move towards the conduction band. And for the p-type doping, EF prime is displaced, that is the Fermi level is displaced towards the valence band. For very heavy doping, EF prime can enter into the conduction band in case of n-type doping, or can enter into the valence band in case of p-type doping, and the semiconductor is regarded as degenerate. That is, it behaves as metal when EF prime enters the conduction band, and it behaves a perfect insulator when EF prime enters the valence band. So these are the two extreme pictures of the semiconductor with the heavy doping of the n-type material and the p-type material. Suppose that a valence electron is moved to a conduction band by pumping. Pumping means that you illuminate with some light source. That is, you illuminate the semiconductor with some light source, or you can you can bombard some electrons to impart energy to the energy of the semiconductors. Then you see that this process is called pumping. Suppose that a valence electron is moved to a conduction band by pumping. Intra-band relaxation, that is the relaxation within the same band, which involves electron-phonon collisions with a time constant of the order of picosecond, is much faster than the interband relaxation. Interband relaxation means that the relaxation from one band to the other band, that is, for example, from the conduction band to the valence band, that is called the interband relaxation. And when we are talking about an intra-band relaxation, it means that the relaxation from the conduction band to the conduction band, or from the valence band to the valence band. And you see that intra-band relaxation involves a very short time of the order of a picosecond. So this is very high in probability that the intra-band relaxation will take place, because it is much faster process than the interband relaxation, which involves a time of the order of nanosecond. So it is a slow process. So the faster process is the intra-band relaxation. So this will occur more quickly in comparison with the interband relaxation, which involves electron hole recombination with a time constant of the order of nanosecond. So intra-band relaxation involves electron-phonon collisions, whereas the interband relaxation involves electron hole recombination with a time constant of the order of nanosecond. Thermal equilibrium within each band will be established even when there is no thermal equilibrium in the semiconductor. So in this case, you see that the overall semiconductor material is not in equilibrium, but the individual bands are in thermal equilibrium, which means that the population will be equal. That is, the population is not changing. Let's designate FV and FC as the occupation probabilities for the valence and for the conduction bands respectively, because V stands for the valence band and C stands for the conduction band. So these gives you the probabilities. FV gives you the probability for the valence band to be occupied, and FC will give you the probability for the occupation probabilities for the conduction band. And these two formulas are given. FV as a function of energy EV, that is as a function of a state EV, is equal to 1 over 1 plus e to the power EFV, that is the Fermi energy in the valence band, minus the energy of the state, which we have written minus EV divided by KT. And in order to write this expression for the conduction case, what we need to do is that we need to, number one, change V with C, and second is that we have to shift these two quantities, that is the energy EC will be positive and EF will be negative, that is EC minus EFC. Because for the conduction band, then the EC will be greater than EFC, and for the valence band, then EFP, that is the Fermi energy, will be greater than the occupied states. So we have to talk about in the sense of the Fermi energy level. So this is the formula between the probabilities for the valence band and the conduction band. Only differs over here. That is, we in one of the, that is in the valence band, we have Fermi energy minus the energy of the states or minus the energy of the electron, and in the second case we have the energy of the states in the conduction band minus the energy of the Fermi energy in the conduction band in case of conduction band. So these two formulas should be used very carefully. That is whether we are going to calculate the probabilities of occupancy for the Fermi level, for the valence band or for the conduction band. Then you have to use that which energy is greater. That is, you have to for the Fermi level you have EF, that is the Fermi's energy minus the energy of the states in the valence band, and for the conduction band you are writing that the energy of the states in the conduction band minus the Fermi energy for the conduction band, where EFV, that is the Fermi energy for the valence band, and EFC, that is the Fermi energy for the conduction band, may be regarded as the quasi-Fermi levels. So here we have changed their names, quasi-Fermi levels of the valence and the conduction band respectively. So these are the quasi-Fermi levels because we are now using the semiconductor in the presence of the doping, and these levels are no more in the center, but these will be shifted depending upon which type of doping and what magnitude of doping are we doing. The quasi-Fermi levels mark the boundaries between the zones of fully occupied and fully empty states at T is equal to 0 Kelvin. This is what we have seen, that there are two distinct boundaries at absolute zero, fully occupied or the fully empty. The states occupied by the electrons, filled circles, and the states occupied by holes, open circles, are shown in figure number 68.2 along with plots of EC and EV versus FC and FV respectively. So let me explain this figure. Let me read the caption first. Plots of energies versus K on the left, and plots of energies versus level occupation probabilities at thermal equilibrium within each band on the right side. You see that we are talking about the thermal equilibrium. It means that we are not talking about okay. So let me explain first on the left hand side. You see that we have two Fermi levels. One is in the conduction band and the other is in the valence band. The one point is that let's talk about the conduction band first. You see that there are some states which we have represented it with filled circles. These are the occupied states in the conduction band because the energies of these states lie lower than the energy of the Fermi level, and the Fermi level for the conduction band is represented by EFC. So since the energy of these states is lower than the energy of the Fermi level, quasi-Fermi level for the conduction band, so these states are represented by the filled circles. Now let's talk about the valence band. You see that the energy of the valence band will increase downward as indicated by the arrow, and these will be negative energies because we are measuring the energies below the level of K. So here we have shown two K levels. For this one, we can, for the conduction band, we have shown the K levels, and the energies will be measured positive with respect to K, and here we have shown the K level for the valence band, for which EV will be measured downward. And for the valence band, you can see that now due to the doping, the Fermi level has moved inside the valence band, indicated by the dotted line, and also labeled by the gap by EFV, where EF is the Fermi energy for the valence band under some doping conditions. And you see that the states in the valence band which are above this Fermi level, they are empty states and represented by the hollow circles. And the states which are below the Fermi energy, they are represented by the solid circles because they are the occupied states. So the states below the level of the Fermi level will be occupied, and the states above the level of the Fermi level will be unoccupied. So this picture is valid for both the Fermi levels and for the states within the valence band and within the conduction band. So after explaining these one, let's talk about now the probabilities. On the right hand side we have plotted EC, that is the energy of the states in the conduction band versus the probability of the occupancy of that states, and below we have represented the energy of the states in the valence band and versus the occupancy of probability of occupancy of that states in the valence band. And again you see that when this curve touches at the center of this curve, in the two curves, the Fermi energy, E, for example, for the lower case, EV is equal to EFV. That is the energy of, that is the valence energy, that is the energy of the state in a valence band is equal to the Fermi energy. Then you see that the probability is half in the center and also half in the conduction band case, where the energy of the state is equal to the Fermi energy. Then the occupancy will be 50%, that is half. But you see that if you increase the values beyond that one, what will happen? The probability will decrease on the left hand side of each curve, because the energy is increasing above the Fermi energy. So the probability is going to decrease below the value of half. And if you lower the value of the energies of those states below the energy of the Fermi level, that is the energy of the states lying below the, that is the energy of the states with the energy lying below the Fermi energy, then you see that on the right what will happen? The probabilities of the occupancy will increase, and at the same time EC will decrease for the conduction band and EV will also decrease for the valence band. So this behavior is the same as we have explained for this case. So this curve has also been explained similarly. And again you can assume over here that we are talking about these probabilities at absolute at a temperature which goes to zero. So close to absolute temperature we are presenting these probabilities. The position of the quasi-Fermi levels in each band depend on the number of electrons moved to the conduction band. The position of quasi-Fermi levels in each band depend on the number of electrons moved to the conduction band. So you see that when you move some of the electrons from the valence band to the conduction band, then the population of the electrons in the conduction band will be equal to the population of holes in the valence band. Because the electrons, initially there didn't exist any electron in the conduction band. So all the electrons in the conduction band came from the valence band. So the electrons in the conduction band are equal in number to the number of holes in the valence band. The electron density in the conduction band represented by Ne is then given by. So this is the formula of the probability that we have used in order to compute the number Ne, where Ne is the number, is the electron density in the conduction band, and is given by the integral of rho c of EC multiplied by the probability function Fc of EC multiplied by DEC. So this is the probabilistic formula. We have used the probability formula in order to calculate the electron density. And you know that these are, rho c is actually the density of states per unit volume, and you know that Fc is the probability and DEC is the energy element. For if you want to see the details of rho c, then you should consult slide number 67. Similarly, the whole density NH in the valence band is also given by NH is equal to from 0 to infinity rho v of EV multiplied by 1 minus Fv of EV. So you see that here we have 1 minus this one. multiplied by DeV. So this is what will give you the density of holes in the valence band. Suppose that through a suitable pumping we move valence electrons to conduction band and make the conduction electrons density equal to n. The electron hole density will also become equal to n, because we have moved the electrons from the valence band to the conduction band. The holes created in the valence band are equal to the electrons in the conduction band. So the conduction electron density n is the same as the valence hole density n. Setting Ne simply equal to n, because now n is a generalized valid both for electrons in the conduction band or the holes vacancies in the valence band. In equation number 68.4, that is, we are using Ne by n in equation number 68.4 and making use of equation number 67.14 from the previous slide, in which we have defined the value of rho, and using equation number 68.3 we obtain the following formula. So let me show you equation number 68.3, this formula, because we are using the value of Fc. So in these formulas we are using the value of rho c from the previous slide, we are using the value of Fc from equation number 3, and then making and then substituting in equation number 68.4 and then solving, we are getting this relationship, where Nc is what we have defined. You see that this relationship in equation number 68.6, the above relationship is capital N is equal to 2nc over pi square root of pi multiplied by the integral from 0 to infinity. Then we have the square root of epsilon, integral is with respect to d epsilon divided by 1 plus e to the power epsilon minus ef. Or you can say that e minus ef. This e is actually epsilon. You can either read it as e or you can either read it as epsilon. So e minus ef, and then you have at the numerator you have square root of e, and integration is with respect to de or d epsilon, where nc is equal to 2 into multiple into 2 pi mc kt divided by h bar square whole raised to power 3 by 2, where epsilon or the simple energy is given by EC over KT, because we have this normalized value epsilon, and then we have this Fermi energy in the epsilon, and the normalized form represented by EF or epsilon F is equal to EFC divided by KT. So substituting these values we can find, but you know that if you substitute these values over here, for example in this integral, the integral is with respect to d epsilon. It means that the integration limits also from 0 to infinity. So it means that if you solve this integral, the epsilon will disappear from the integral, from the integrand, and what we shall get after that, we shall solve in the integral, we shall only get that this integral will have a value that depends upon the value of EF. Then you see that EF will depend upon the value of N and NC. So if you move NC on the other side, you will have N over NC. So here you can see that from equation number 60.6, that after solving the integral, you will see that this shows that EFC, that is the Fermi energy divided by the KT, depends only on the value of N over NC. And you know that this ratio, that is EFC over KT, is actually EF. And I told you that when you solve this integral, you will survive with only the value of EF. So EF or EFC divided by KT depends only on the value of N over NC. You see that NC is what I have described over here, and capital N. So if capital N is known, you can find out the level, you can find out the Fermi energy. The quasi-Fermi energy for the conduction band represented by EFC can be determined if the concentration of the injected electrons into the conduction band is known, that is capital N is known. An equivalent expression for the valence band can also be obtained by replacing the suffix C with V in the equation number 68.6. So you can also modify this equation for the case of the valence band, and you can also determine the position of the Fermi level in the valence band. So you see that this is what we have explained: the Fermi level in the semiconductor without doping and the Fermi levels in the semiconductor with doping, with the p-type doping and with n-type doping. We have explained the Fermi, we have explained, and we have also explained the probabilities of the states in the conduction band and in the valence band, how they would change when their energies are lower than the Fermi energy or greater than the Fermi energy. The simple rule was that if the state of energy is greater than the Fermi level, then that state will be unempty. Then that state will be empty. And if if a state has an energy which is lower than the Fermi energy, then the state will be occupied or has a significant probability of occupation, because we have drawn the curves of the probabilities that the levels will be occupied. And when the energies are much lower than the Fermi energies, then the probability of the occupancy of such states approaches 1, as we have shown in this diagram also. So this with this one it completes the answer. So this is the end of slide number 68.